Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. Today, what's the menu? We are going to finish this MapReduce. That's the first generation of massive parallel processing. And then we look at the second generation known as Apache Spark. But before we start, I have a question for you because we already looked a little bit into MapReduce. And my question is the following. You have just submitted a typical MapReduce job onto a large 1,000 node cluster. That's important. What do you do? A, it's done before you ask. You go check the results. B, you go for a cup of coffee. It will be there when you are back. C, you switch to something else and we'll check again in a few hours or even tomorrow. Or D, you hide from the CFO. It's interesting because there is a majority leaning towards real time or near real time. Okay. All right. So it's funny, nobody hides from the CFO. Sometimes there are people in the room with work experience who know how much it costs to use a cluster. Anyway, this one was only a joke. So the third answer is correct. You switch to something else and we'll check again in a few hours or tomorrow. This is not real time. This really takes a lot of time. When you have a machine, a cluster with 1,000 machines, you launch the job, it needs to be set up. You have to have all the mapping phase, then the shuffling is going to take a while as well, and so on. So it really, really takes a lot of time. And so it's very typical to have jobs that run for a couple of hours, sometimes even days or even weeks. That's borderline machine learning applications, then that it can go for weeks or months. Anyway, so real-time MapReduce, you can forget about it. That is not the architecture of MapReduce, right? If you want things in real time, typically for lookups and so on, we will see in a couple of weeks. You can do this with indices and with other means, but MapReduce is really something that takes time and to have in mind. All right, but even though it takes time, it does things you could not do on a single laptop. Because on a single machine, on a single laptop, it would just take forever to read everything from the disk sequentially. But on a cluster, you can read everything in parallel. Okay. All right. So let's now continue. I will directly go to where I left you last time. So you remember that MapReduce is made of a mapping phase, a shuffling phase, and a reducing phase, and that every phase takes in a collection of key-value pairs and spits out a collection of key-value pairs, right? So it's collections of key-value pairs all over the place. The mapping phase is in parallel, the reducing phase is in parallel, but the shuffling is all the spaghetti where all the intermediate data flows around the cluster. But there is one problem with that. It's that it needs a collection of key-value pairs as input, and it needs to spit out a collection of key-value pairs. Now, the problem is that not everything in the world is a collection of key-value pairs. And you know the saying, when you have a hammer, you tend to, everything in the world looks like a nail. And so when you look at MapReduce, when you have MapReduce, everything in the world looks like a collection of key-value pairs, right? And so I need to tell you how in real life that works, and you will see it's quite natural to do. For example, if you take a relational table, typically in a relational table, there's going to be a primary key that might be made of one or more columns. For example, in a list of persons, the primary key would be the social security number. That would be the column in grid here. And that naturally gives you a collection of key value pairs because every key is basically the social security number, the primary key, and the value in the pair is all the rest, all of the other columns, right? So it's quite natural to turn a relational table like this into a collection of key value pairs, and then MapReduce will know what to do with it as the input of the map phase. HBase, it's the same. It's quite natural in HBase that you consider that the row IDs are the keys, and then everything else, all the column families that you're interested in, doesn't need to be all of them, but all the cells in the column families would be the value, right? So far, so good. That's natural, right? So the row IDs, the primary keys are the keys. The other cells are the values. Now, what if we don't read from a relational database system and we don't read from HBase, but instead we read from S3 or HDFS or Azure Blob Storage, and what we are reading is a text file. So if you're reading a text file, it doesn't look like a collection of key values, right? But you can hit it hard enough that it becomes a collection of key values if you use the new lines. So every time there's a new line, you basically separate, and every line will give you a key value. And then you put the line in the value, the entire string of the line in the value. And for the key, you can put the offset in the file. So the number of characters since the beginning of the file and until the beginning of the line. So here it's an offset of 0, because that's the beginning. Here it's 18, so you could count 18 characters, starts here. And so you see that we turned a text file, assuming there's lines, right? Assuming there's plenty of lines, we turned the text file again into a collection of key value pairs. And once again, this is something MapReduce is going to be able to process. Now, there are also cases where you have a text file that is not really just text, like it's not just Sherlock Holmes, it's actually text that was written by sensors or like at CERN or temperatures for weather forecast. Then it's very typical that it's naturally in a key value fashion, or maybe you make it in a key value fashion, just with a special character. Can be a comma, a tab, a colon. Here I just put a black circle, but it doesn't really matter. And so you take that, everything on the left is the key, everything on the right is the value, right? So that gives you the key value here, here the key value, and so on. Oh, that's just a formatting thing, probably with the conversion to the software. So here, if you don't have the symbol, then you just don't have any value. And here you have the key and then the value, right? If you forget about the formatting. All right, so that is another way to convert text to a key value. You can also do that. And finally, there is also a file format that is native to MapReduce. It's been invented with MapReduce that is natively a sequence of key values, right? So you store it, that's called a sequence file, and it has inside a sequence of key values. And the advantage is that it's fully binary, and when you put the keys and the values in there, it preserves the types. Because if you do a program in a MapReduce job in Java or in another language, your keys will have specific types, integers, dates, strings, and so on. Your values will have specific types as well. And so you can just spit them out in a sequence file. And that format is actually used also by MapReduce to store intermediate data on disk, right? So sequence files are basically native to key value pairs, collections of key value pairs, just like formats like Parquet are native to data frames, right? Okay, so you have that too. And this is the example I gave you last time with, because somebody requested one. In order to count words, you can have a mapping phase that basically tokenizes. See, I simplified with spaces, so we cut with spaces. And I output intermediate key values using each word as a key and one, because every time you count one occurrence of one word as a value. And you see here that as a user, you can pick your mapping function, right? You do whatever you want. And in particular, I can decide that my intermediate key is the word and my intermediate value is the count. And then the reducing function takes a group of key values with the same key, so the same word, and then it adds or it counts the ones, which is the same because it's only ones, and outputs the total count of lorem, which is 7. Who is with me? Right? Okay. Here's another example of what we can do. What if I want to filter lines? I have like all of Sherlock Holmes, and I want to find all the lines on which I have very specific words. So that I can do with a map function that either outputs the input key value unchanged or doesn't output it, right? It's just a filter, doesn't modify anything, doesn't create anything, it just filters out. So for example, the first line contains the word we are looking for. The second, third ones do not. So I just drop these key values. I don't output them as intermediate key values. And the fourth one matches my predicate, contains the word I'm looking for. And so I output it. So this is a special case in which the intermediate collection of key value pairs is a subset of my input collection of key value pairs, right? I just filtered. And can you guess now, since that's already what I want, what will I put as the reduce function? Since I already have what I want, yes? Exactly, I just output as is. So my reduce function here is just the identity, right? I don't change anything because the map phase was enough, right? Because filtering things is something that runs fully in parallel. So the shuffling is totally useless. In fact, MapReduce has an option that tells it there is no reduce, don't even bother shuffling, right? And then it's even for performance, it's good because there's no spaghetti in the cluster. All right, so that's for filtering lines. You might have in mind that filtering lines is kind of the where clause in SQL, right? That's basically a selection in the relational algebra. And it's not a surprise because MapReduce will be used for the relational algebra. So in fact, we've just implemented a selection. So since we've implemented a selection with MapReduce, what if we try to implement a projection with MapReduce? So imagine that I have JSON lines in my input, and I would like to project this to specific fields, right? So the first thing that you should be aware of is that MapReduce doesn't even have the slightest idea of what JSON is. MapReduce just sees key values. That's it, collections of key values. So to MapReduce, this in fact will be just strings, right? So it will see that. So now, if you want to project, you can do it with a map because every object will be projected to only some of its keys. So let's say we project to ID and country. So the field A is going away. That goes fully in parallel, right? Projecting. All you do is object by object, you remove it. What is important to keep in mind is that this map function here involves parsing the object as JSON, projecting, and reserializing as a string. Because again, MapReduce doesn't know it's JSON. So it's you as the user that have to put the logic to parse JSON and project it and reserialize it as a string in your map function, right? But you can do it, right? So now we can do a selection and a projection. What would be the reduce function that goes with it? Again, identity. Why? Because we already have what we want. We already done. After the map phase, we already have the projection of our data set. So for the reduce, we just keep it as it is. And we will even tell MapReduce, don't even bother shuffling. We already have what we want, right? So we know how to select, we know how to project, and they don't even require any shuffling or any reducing, right? It turns out, but that we'll get to it a little bit later, especially in Spark, that you can also implement group by, you can implement order by, you can implement like many of the primitives, joins, Cartesian product, and so on. It all works. You can do it with the same similar techniques, even though, as you might imagine, when you group by and when you order by, there will be shuffling because you cannot just group and order without shuffling, right? Okay, so that was a couple of examples, how to count words, how to filter selection, and how to project. Now, the next step is a question that somebody asked last time. I think it might be on the chat. Is there any way to optimize things? Because the shuffling is very expensive. That's a lot of intermediate key value pairs that get shuffled over the network. Can we optimize that? The answer is yes, absolutely, we can optimize that. So how do we optimize things that get shuffled over the network? Well, what you could do is reduce the quantity of what gets shuffled over the network, right? So imagine you have 1 gigabyte that gets shuffled around. If you manage to bring it down to just 100 megabytes, then that's less to shuffle around, right? And that's going to be more efficient. So indeed, yes, absolutely, there is a way to reduce the quantity of data that gets shuffled around. That's called combine. So here's the idea. That's a typical job in MapReduce. I told you in 80% of the cases, the type of the keys and the values are the same for intermediate and output, in 80% of the cases, not always, but very often. And so in that case, it turns out that there is an easy way to optimize. We can basically, during the map phase, combine some of the intermediate key values into less intermediate key values. In fact, we've already done it with the Pokemons, but I will show you. So the idea is that, let me explain with the Pokemons. Imagine that I distributed the Pokemons to everybody, and now, instead of counting locally the Pokemons, you could have output Pikachu and all the others just with one, just like the way we count the words, right? But then you would have shuffled around pairs of Pokemons together with a one. That would be a lot. That would be as many pairs as Pokemons, right, to shuffle around. But in fact, that's not what happens with the Pokemons. Imagine that somebody got a set of Pokemons and had 7 Pikachus. So instead of outputting 7 key values, Pikachu 1, Pikachu 1, Pikachu 1, Pikachu 1, 7 times, they will instead output Pikachu 7, right? In fact, that's combining. What they are actually doing is taking the Pikachu ones, the 7 Pikachu ones, throwing them away and replacing it with Pikachu 7, and it's the Pikachu 7 that's going to get shuffled around. So you see that that's less key values that get shuffled around. And this is called combining. Combining comes with no guarantee. You basically, as a user, provide a combining function, like the function could be if you have the same Pokemon with several counts, then it's okay to replace all the key values with just one that has the sum of the counts. And that you can apply whenever you flush to disk. So imagine that you have all your pairs of Pokemons associated with ones. When you flush it to disk, instead of flushing the Pokemon and the ones, you basically flush the aggregated key values. For whom is that clear? Right? So you directly flush the combined key values. And the same when you compact, you can do it again. What happens a lot is that the combine function is going to be the same as the reduce function. Doesn't have to be that, but it's very often the case. For example, in the case of the Pokemons, the reduce function was that you take key value pairs for the same Pokemon and you do the sum of the counts, right? You do the sum of the numbers. Well, in that case, the combine function can do exactly the same thing. So whenever you see key values with the same Pokemon, you just sum them and replace with the sum. And the reason it works is that addition is commutative and associative. If you have numbers to add, you can add them in any way you want, right? It doesn't matter. You will always receive the same, you will always compute the same sum. If I say 1 plus 2 plus 3, then you can say 1 plus 2 and then plus 3, or you can say 1 plus 2 plus 3. It doesn't matter. So this is the reason why, if we have something like this, we can use the combine function that does the same as the reduce function. But in order to do that, first, it must be the case that the types are the same for the intermediate and output values. And the reduce function, I put it in quotes, must be commutative and associative. If you want to state it rigorously, it should be that the reduce function aggregates the values with a binary operator that is commutative and associative, like plus, like min, like max. These are all commutative and associative, right? And so that's called combining. The idea is really that you compute very early. You try to compute as much as you can, as close as possible to the data. right? And so the combine is in the map phase, so it's very, very close to the data, and you want to reduce the amount of data that flows over the network. Here's an example, just in case some of you might not have understood it yet. Here's an example. That would be the naive approach with Pokemons or words that you only output one key value for every word saying you saw it once. And then this is the reduce function that computes the sum of all of this. Addition is a binary operator that is commutative and associative, right? So I can use it for combining, and you see that it does not change the result, right? So if I take my intermediate key value pairs, and already during the map phase, when I flush or when I compact, I already eagerly aggregate some of the key values, then maybe instead of shipping this over the network during the shuffling phase, I throw that away and I send this over the network during the shuffling phase instead. That's much less. And then in the reduce phase, I will have less to compute. However, the results are the same. If you had called reduce over this, you would also have gotten 7, just like on this. And same here, you find 6. 4 plus 2, you would also have found 6 in here. It does not change the results. But by eagerly aggregating the intermediate key values, we reduce the size of what gets shipped over the network. For whom is that clear? Right? That's a very fundamental trick in big data to try to eagerly compute things to reduce the size of what you send over the network. Okay. Now I will quickly show you what it looks like in Java, but very quickly, because that you can see in the exercises in practice. So MapReduce can be done in Java, but in many other languages like Python and so on. So it's compatible with a lot of languages. What do you need to do? Well, you just need to supply the map function, supply the reduce function, say where your input data is, and say where you want to output your data to. It's that simple. And optionally, you can specify a combine function if you want. So that's an example in Java of a map function that takes a key and a value, and you can output as many as you want by calling this method. Here's an example of a reduce function that takes one key plus all the values associated with that key, so that's the intermediate key values, and then outputs the output key values. And then once you have written these two functions, map and reduce, then you tell MapReduce, this is my map function, this is my reduce function, this is where my input data is, and this is where I want to write my data to, right? So all of that you can tell in your code. You can give a name to your job so that when you go to the website and monitor your job, you see the name of your job, and then you wait. That simple, okay? That's another example where I also specify a combine function. And in that case, I reuse the same function as the reduce function because it has a binary operation that's commutative and associative, for example. Yes? So it's just to repeat the question. So this is about controlling the frequency of the combining, right? So you have no control over the combining. This is, you specify the combine function, and then you trust MapReduce for using it whenever it sees fit. It might be that it doesn't use it at all. Could be. It could be that it uses it a lot. Could be that it uses it just once. But this is out of your control. You cannot deterministically micromanage MapReduce by telling it exactly when it's supposed to use it, right? It's just out of courtesy, you can tell MapReduce, by the way, here's a combine function in case you need one, and then it does whatever it wants with it, right? You just need to make sure that it's mathematically correct, meaning that the combine function you supply doesn't modify the results. Then that's up to you to basically make sure of that, right? So that doesn't really answer the question because that you cannot, right? But yeah, you cannot micromanage MapReduce to that level. So it decides, for example, whenever it flushes, whenever it compacts, it can use the opportunity to combine. These are good points to do it. occurrences of when it might not use it is that when it just puts the key value pairs in memory, but there's not a lot of data and it doesn't find it necessary to actually combine anything, right? It might also just say, okay, I'm leaving the data as it is because it's not worth it, right? But what's really nice is that as the user of MapReduce, you don't need to care because that was figured out by the implementers of MapReduce. It's all part of the MapReduce library that it decides when and when not to use it, right? So it's something you don't need to worry about, right? Okay. If you need to define your own architecture or tweak it, you're already a power user, an advanced user, and in fact, you might be redefining a new platform, right? And this is in fact what the Spark, Apache Spark actually did, right? So you do have a lot of things you can tweak in MapReduce. So there's a lot of configuration, but we'll see that it has its limits, right? At some point, you realize that it's not enough, and you need more modern software. Right. It's already, yeah. Do you have another follow-up? Okay. It's already 20 years old, MapReduce, right? So a lot of things have happened since then. Okay. Now, I would like to take the time to go more into the finer-grained details of what happens inside MapReduce so that it's crystal clear to you. The reason I'm doing that is that if you go to the internet and search for MapReduce and you see people on Stack Overflow or talking about MapReduce, you will see that the people talk about mappers and reducers. They say the mappers do this, the reducers do that, and the mapper do this, and the reducer do that. You should not do that. Do not use the words mapper, reducer, combiner, even less. Do not use them. Instead, I would like to encourage you to more precisely talk about map slots, reduce slots, map tasks, reduce tasks, map face, reduce face, map function, reduce function, combine function. And you will see that paying attention to the words you use will give you clarity of mind. Then you will actually understand what's going on. And I have a few animations to show you that. So I repeat, do not ever, ever, ever say mapper, reducer, combiner. That you ban from your vocabulary. Unfortunately, you still have to read people that do that, and then you have to figure out what they mean, but do not do that. Right. And I'll make sure to also tell the TAs that in the exam, like no mapper, no reducer, no combiner, right? All right. I'm going to use an analogy for that. Imagine that a couple of friends went on vacation far away, and they want to send postcards to all their friends. 50 postcards. The thing is, they don't all write with the same speed and so on, so they want a bit of flexibility. So they are going to sit around the table. The postcards are in the middle of the table in 3 groups. And they are going to split the postcards into 5 splits. That corresponds to the HDFS blocks or the partitions, right? So the first thing they do is 5 piles of 10 postcards on the table. These are the splits. Now, every split is associated with a task. The split is the cards themselves. The task is a to-do, it's some homework. So the task associated with the first split is to write on postcards 1 to 10. Hello, dear friend, we are on vacation here on Mallorca, and we send you our greetings and so on. We're having a lot of fun. So that's the task. You write on the postcard, you write the address, you put the stamp, and then you're done. And then you have as many tasks as splits. So far, so good. So these are called tasks. A task is an assignment. It's a to-do. So once they have established that and they have the splits on the table, what happens is that each group, each one of the 3 groups takes a split, right? So 2 of the splits are not used yet. They each take 1 split, 1 group of postcards, and it means they have to do the task, accomplish the task of writing on the postcards, right? So first group, 1 to 10, second group, 11 to 20, third group, 21 to 30. Now, there is an unfair advantage in the second group because there's 2 of them, so they're actually maybe going to be done first. and already put back the intermediate data, which is actually the postcards with the words written over them and the stamp over it, they're done. What do they see? What do they do? Well, naturally, they are going to take another split because their split 4 and 5 are still not done. So dynamically, without waiting for the others, the second group is going to take the next task and start working on it. Right? Then maybe the third group is done. What do? They take the remaining split, right? That's done. And then maybe the second group finishes, but now there is no split left, so they just wait from now on. They have to wait until the others are done. So they stop doing anything. Then maybe the first group is done too, so they also wait because there's no more tasks available. And finally, the third person is done with the last split, right? So the tasks are the blue rectangles. It's to-dos. What we will call map slots are the 3 groups. The people would be slots. It's a person who is capable of carrying out a task, right? So in our case, it's going to be CPUs. And what you notice too in here is that there are more splits than slots. There are more tasks than slots, right? You notice that we had 5 piles of postcards for 3 people, but that's good because then, since they don't take the same amount of time, the people who are done earlier or who are a bit faster will have more splits, right? So this is the trick. So now that I have taken this analogy, that should help in your minds, coming back to MapReduce, a map function is a function in Java or Python, or you can see it as a mathematical function that takes one key value and outputs 0, 1, or more intermediate key values. That is a map function. A reduce function takes a group of key values that all have the same key, complete group, all of them, and outputs 0, 1, or more output key values. The combine function also takes a group of key values that have the same key and outputs 0, 1, or more intermediate key values, typically 1. So these are the functions, right? Then the tasks. A map task, it's like the postcards, when your job is to write on 10 postcards. A map task corresponds to a split, so it's a partition of the data with plenty of input key values. And a map task consists in sequentially calling the map function on every key value pair that you find in your split. Sequential. So imagine that I was given a split or a partition with 3 key values. Then I call the map function on the first key value. After I am done, I call the map function on the second key value. And after I am done, I call the map function on the third key value. It's not in parallel, it's sequential. Because right here, I'm talking about one person, one CPU, one core. Right? So it's not parallel, it's a sequential series of calls. This is a map task, right? Sequential calls to the map function. A reduce task, that's the same thing, it's a sequential sequence of calls of the reduce function. So a reduce task might contain several groups of key values. Each group has the same key. And sequentially, one after the other, I'm calling the reduce function on each of these groups, outputting every time 0, 1, or more key values. Who is with me? Right? Sequential, that is a task. A task is a sequential sequence of calls of the function. Combine task does not exist. You do not call the combine function sequentially or anything. The combine function is only used whenever the engine sees fit to optimize the size of the intermediate data, but that's not a task, right? It's totally different. Okay. Then that's how it would be done. Basically, at the end of a map task, you might want to reduce the size of your output by calling the combine function, right? But that's not a task. All right. Now, a map.
Sorry, there's
slot.
a question.
Yes?
So the question is, for each of these tasks, does the function, right, you call a function for each key value pair, does the function have to be the same within the task?
Yes, absolutely. The map function is always the same. That is the function that was supplied by the user when they started the job. right? So the user starts the job, they say, this is my map function, one and only. This is my reduce function, one and only. And here, it's always, always, always the same map function that was provided by the user, right? Always the same one. But you just do them one by one on every key value. Does it answer your question? Yep, awesome.
Yes.
All right. So the task, sequential calls of the functions, same for map and reduce. Now, map slot. The map slot is going to be a CPU core, right? Or a person in the case of the postcards. So you know CPU, central processing units, that's the brain of your computer. You know by now that the CPUs have several cores, right? There's been a lot of ads on television regarding this, right? So every core can act on parallel. So now I'm looking at one core of my CPU that can do one thing at a time. One core, one map slot is going to sequentially process tasks. And in every task, you sequentially call the map function, right? So it's a sequential processing of tasks. And again, one after the other. You take task one, you're done. You take another task, two, you're done. Take another task, three, you're done. Sequential, right? It's one CPU core. So at that point, you might be wondering why do you keep telling us it's in parallel, right? But this is coming, the parallelism, right? But for now, it's just sequential. It's one person writing the postcards one by one. Same for reduce. You have a reduce task, then you're done. You take another reduce task, you're done. You take another reduce task. That is called the reduce slot. It's again a CPU core, but it's a CPU core that's reducing. Combined slot doesn't exist, right? You only have map slots and reduce slots, but combined slots do not exist. And finally, the entire map phase, that's when you look at your entire cluster, you have 1,000 machines, maybe there are 10 CPU cores on every machine, that gives you 10,000 slots. The slots are going to perform their tasks in parallel, right? It's like the postcards. At first, they each pick one task. Every slot picks one task. And when they're done, they pick the next task, the next task, the next task, until no task remains. For whom is that clear? Right? So it's dynamic. So you do not know in advance how many tasks every slot is going to process, because it depends how fast they are. Right? The faster they are going to be with the first tasks, the more tasks they are going to obtain. And that's the magic of MapReduce. And that is the reason why in practice, it's always a good idea to have more splits, and hence more tasks. There's as many tasks as splits, more splits than slots, right? So that you can have this dynamic allocation of tasks to the slots. That's it. That is the overall physical structure of MapReduce. The same goes for reduce slots. So after that, you shuffle, right? Then you have all the reduce slots that also take their reduce tasks one after the other, but in parallel. Every slot acts in parallel to the other. That would be 3 in that case. So you saw probably the third slot was slower than the others because the slot 1 and slot 2 had enough time, where completed their tasks earlier and could take care of another one. Okay, who is with me? Right? So this is fundamental. This is a deep understanding of what actually MapReduce is doing. Combined phase doesn't exist. Right? Combine is only a function. Okay. So in fact, if I summarize, this is what it looks like. You have your machines. Every machine has several cores, so several slots, and every slot consists in processing tasks one after the other, and every task consists of repeatedly and sequentially calling the function. And every slot can be a mapping or a reducing slot. Right. Okay. Yes? When are they all together? Oh, so they never get merged into a final results, in the sense that every reduce slot is going to write files to HDFS. And typically, every time you're done with a task, the output of the task is an HDFS file. At no point do you merge these files, right? So it really means that every reduce slot is a client of HDFS. and writes their files in parallel without talking with each other. Right? Does it make sense? Mm-hmm. Yeah.
How does the reduce part that is processing first and the pages that Julia also has the last one?
Okay, I see. So the map slots are going to process the input splits, so the pages, only the map slots. Because between the mapping and the reducing, there is the shuffling. And so what happens is that during the mapping phase, the reduce slots are completely idle. They don't do anything. It's only the map slots that do it in parallel. Then what happens is that the words that appear in plenty of different, that are seen by plenty of different map slots, when you do the shuffling, the same word will all be redirected to the same reduce task, and thus the same reduce slot. Right? Then it means if it's too many, so I'm repeating also on the microphone, if you have so many key value pairs that the size of the reduce task is impracticable, then it means whoever designed the job should do it again. Right? It's basically, you have to keep it in mind that when you create a MapReduce job, you have to be careful that the amount of data you will have in the same group doesn't grow too big, right? And so in that case, you need to stop everything, maybe go in front of a whiteboard and see if you can modify your algorithm, the MapReduce algorithm, right? I mean, your functions. You might get memory overflow or disk overflow. Well, memory overflow, you can still spill to disk, but at some point, it might either go very slow because it keeps writing and reading from disk, or it can just at some point just start, okay, I cannot do it anymore, and bam, you get an error. And then you really, as the user, need to rethink your approach, right? It means that you're not using MapReduce the right way. If it ends up like this, that a reduce task would be too large. Okay.
So we have some questions on Zoom.
Yes.
First, a clarification. Could you clarify why there is no combined task?
Oh, wait, there is non-combined task because the only purpose of the combined trick, it's an optimization. The only purpose of the combined trick is to offer an opportunity to MapReduce to reduce the size of the intermediate key value pairs. That's all it is. It's not, at no point do you organize calling the combine function in parallel on anything. That's absolutely not the intent of the combine, right? The combine is something that whenever a map slot is flushing some key values to disk, then it can reduce the size of these intermediate key values by calling the combine function, right? That's how it's intended to be used, right? But there is no combine phase or combine slots or combine tasks. Does it make sense? Right? It's only an optimization. It's only to reduce the size of the intermediate key values.
Yeah, and there's another two questions.
Yep.
So in practice, for each of task, no, okay, sorry, I phrased this wrong. So in practice, do you use different map or reduce functions across different tasks, or is it the same?
Always the same. If you have one MapReduce job, there is only one map function and only one reduce function, only one for the entire job. However, you could have a MapReduce job and then another MapReduce job that takes the output of the first job as its input, right? Then you could change. But for one MapReduce job, and right here we're looking at only one MapReduce job, there's only one map function, only one reduce function, always the same one, even across tasks, even across slots. Right?
And the last question, I guess, is regarding randomness. Mm-hmm. So the question is, do you use the same random seed across all tasks? I think he's also asking regarding shuffling, but maybe there's also random seeds in shuffling.
That is an advanced question. I think that could be useful when you do that, when you write tests, for example, when you want to test and you need to always have the same predictable results, right? I think you need to distinguish between the seeds that MapReduce would use internally and the seeds that you would use in your own code, right? So if you need to have random functions in your map function, then you basically need to ensure that you use pseudo randomness and then you put the same seed everywhere, right? I'm not sure if that's answering the question or if you meant the internal randomness of MapReduce.
Okay, so they clarified what they meant is, are all shuffles random across tasks?
So the shuffling is in between the tasks, right? So you basically have your map phase with the map tasks, and then you have the shuffling, and then you have the reduce tasks. And what is going to happen to decide which key belongs to what reduce task? Then you use indeed the hash. It's called the hash. That would basically be a form of pseudo randomness, but you use a hash function that is a way of telling, given a specific key, it belongs to reduce task number 1 to reduce task number 10, right? Who knows what a hash function is? Right, some of you. So hash function is basically like a mixer. It's a way of very quickly extracting some number from anything, right? And so once you're done with the mapping phase and you need to decide what reduce task contains what intermediate keys, you do that with a hash function, right? So the hash function assigns every key to a specific reduce task number, right? Does that make sense?
Yes.
Yep. Awesome. I think the time has come for a break. I'm actually almost done with MapReduce. I have one last thing I will tell you after the break regarding splits and blocks, MapReduce splits and HDFS blocks. If you have more questions, of course, I'll answer questions. So I'll see you. It's already 2 past, so I'll see you at 17 past 9. So you have the break to the full extent, right? So see you in 15 minutes. Hello? Yes, of course.